Now this one is about the quantum harmonic oscillator. Now it relates to the Schrödinger equation. The total energy of a system expressed in terms of momentum is this here. Is the classical Hamiltonian. Applying this the conversion rules here from the classical to quantum, we get a Hamiltonian given here, which is the h hat you find in the Schrödinger equation, and expressing this in terms of the frequency here, it gives us this as our Hamiltonian. And finally, inserting the Hamiltonian into our Schrödinger equation gives this. A stationary state wave function takes the form of psi of xt equals psi of x e to the minus I e t over h bar. When the energy eigenfunction psi of x satisfies the time-independent Schrödinger equation, we get this. The energy eigenfunctions of a harmonic oscillator are given here, where once again our frequency is root c over m, and this is the classical angular frequency, which are energy levels of the oscillator. Energy levels are equally spaced, starting from h bar omega 0 over 2 with constant spacing of h bar omega 0, and h bar omega 0 over 2 is called the 0 point energy. Now let's go with an example. Examples show that this wave function is an energy eigenfunction for a harmonic oscillator, provided positive constant A is appropriate. And find a suitable value for A and determine energy eigenvalue. We substitute this in the time-independent Schrödinger equation as such, and taking the derivatives and cancelling, we get to this term here. Setting x equals 0, we get the energy level of a h bar squared over 2m a squared. Then x does not equal 0, we get this a to the 4 h bar squared m squared over omega naught squared. So a suitable value of a is this, which confirms this is an energy eigenfunction with corresponding energy eigenvalue here. Now higher energy functions, or the energy eigenfunctions in a harmonic oscillator of the form constant multiplied by a polynomial in x over a multiplied by a Gaussian function e to the minus x squared over 2a squared. In the ground state, the polynomial equation is equal to 1, but higher energy eigenfunctions have increasingly complicated polynomials. The Gaussian function always stays the same. The polynomials that appear in the harmonic oscillator are called harmonic polynomials. And the energy eigenfunctions are usually written in this form, where hn x over a is the nth harmonic polynomial in x over a, and cn is a normalization constant as always. In general, hn x over a is a polynomial of the order n, so the highest power of x over a that appears in it is x over a to the n. Only even powers of x over a are present when n is even, and only odd powers when n is odd. Now the first few harmonic polynomials, hn, x over a, and the normalization constants are given here, which you could look up in any textbook or basic formulas like solutions online. Now we'll solve the time-independent Schrödinger equation. We already, from the last lecture, we've shown this. So we have here h bar squared over 2m equals this, and 1/2 m omega squared equals this. So these two equations allow us to write the time-independent Schrödinger equation for a harmonic oscillator in this form, where the Hamiltonian is given here. This is equation 1. The two This consists of two terms. The first, proportional to x squared, is the potential energy term, and the second, proportional to derivative of partial derivative with respect to x squared, is the kinetic term. For a specific axis, the potential derivative becomes a total derivative. Now we factorize the Hamiltonian. Now, equation 1 looks like a difference of two squares. Any difference of two squares can be factorized in this form from basic algebra. Now, equation 1 is similar, so we consider this acting upon a function of x. Now, multiplying out the brackets, we get this. And notice the third term requires differentiating a product of x, f of x. Now carrying this out and cancelling gives rise to this equation here, and hence this. Now we can express this as an identity between operators, including the 1/2 that appears in the Hamiltonian. We have 1/2 of this here. And we see that factoring almost works, but we have a remainder of 1/2. We can also take the two factors in opposite order, and almost identical calculation gives this here, where remainder is minus 1/2 in this instance. These factorizations are useful. They become the operators A, and this is a little like a crucifix symbol, a hat, dagger, I think these are called daggers, and a hat. These are the raising and lowering operators respectively. With this is the raising and this the lowering. In regards to energy levels, these are. Now using these along with the equation here, the Hamiltonian operator can be expressed in this form. Where A and A bar are the first order operators. So we have expressed a second order differential operator of the Hamiltonian in terms of two first order operators. Now subtracting the equation with the remaining plus 1/2 factor from the equation with the minus 1/2 factor gives this, which means that the lowering and raising operators are operating on a function of x are not equal to the reverse. So now this is Dirac's reasoning. The eigenvalues of and eigenfunctions found by solving the time-independent Schrödinger equation, we use this operator here to express the Hamiltonian in terms of raising and lowering operators. Then the time-independent Schrödinger equation takes the form here. The first rung on the energy ladder. The above equation would be satisfied if the A hat of x equals 0 and E equals 1/2 h bar omega 0. Writing out this operator equals 0, A hat operator equals 0 in full, we see that the operator equals 0. This gives the first order equation here with solution here. Now climbing the energy ladder using the raising operator, which as the dagger, we will show that this is also an eigenfunction of the Hamiltonian with a higher eigenvalue than psi of 0, which is the ground state. To do this, apply the Hamiltonian to a hat dagger, and the Hamiltonian here. Now they're leaving the order of the operators A dagger and A undisturbed, and remembering that that 1/2 and h bar omega 0 are just numbers, we can pull out a factor of A dagger from the right hand side, giving this. Now operators A hat and A hat dagger in round brackets are not in normal order. This can be rectified by using the commutation relation here, which we derived earlier. So our Hamiltonian operator here becomes this. We know that psi of naught x is an eigenfunction of the Hamiltonian with eigenvalue here, the lowest state, which is h bar omega naught over 2. So we can conclude this. And generalizing this, and generalizing here, generalizing to, so the generalization is from the state naught to the state n. So like basically any kind of order you wish to put into this operator. Now, which shows a hat dagger of psi of n of x is an eigenfunction of the Hamiltonian with eigenvalue here, the energy of the nth state plus h bar omega naught, similar to a hat. Now, a hat of psi on n operator on x is an eigenfunction of that Hamiltonian with the energy value here. And yeah, that's it. Thank you, and please do subscribe.